The first prototype of my Thermoacoustic Stirling was an experimental engine with very little power. Extensive experiments to increase performance have even driven a self-printed turbine. To generate meaningful power, the output needs to be increased significantly, and many of you asked for this in the comments on the last video. I would like to use the Stirling engine to build a micro-combined heat and power unit to support our solar plant in winter and heat the house. To fuel the engine, I produce biogas with a homemade micro-biogas digester that runs on kitchen and green waste. The use of wood or wood gas for firing is also conceivable. We have enough of that as well. For many years I have been developing various Stirling engines, some of which were quite powerful but too complex, expensive and maintenance intensive. With the concept of the Thermoacoustic Stirling engine, I now hope to have found a simpler and, above all, reliable and almost maintenance-free option for use in a micro-combined heat and power plant. The design of a thermoacoustic engine is not easy due to the very complex acoustic theory. Without this understanding, it is also very difficult to use design tools such as delta AC. I'm still a long way from being able to use the theory or delta AC in any meaningful way. That's why I'm making the more experimental approach and trying to scale the original engine. The heat exchangers are the key components in all Stirling engines. The task is to get as much heat as possible into the working gas in the heater and out in the cooler. That's why I've designed heat exchangers that have a much larger transfer surface and are designed for much higher temperatures and pressures. The heater and thermal buffer tube are made of 1.4571 heat-resistant stainless steel. With my self-built electrical discharge machine, many thin slots have to be eroded into the heater to transfer as much heat as possible to the working gas. This takes quite a long time, so I'm making this video while the EDM is working in the background. The two coolers are manufactured in the same way, but because they are shorter and made of aluminium, it is much quicker. The regenerator now has an outer diameter of 37 mm and will hopefully be able to generate a strong acoustic wave. The transition pieces are again from the local hardware store and allow universal connection options for experimenting with inertance and compliance. With this configuration, heating temperatures over 600 degrees Celsius and pressures up to 10 bar are possible. I will also be conducting tests with helium as a working gas. These improvements will hopefully make it possible to drive a generator with a bidirectional impulse turbine or to generate electricity with a linear generator. This allows me to better understand the effects of changes and learn a lot about the behavior of the thermoacoustic engine. It may take a while until I get the first results, but maybe I will make a video about an interim result and see how things progress. Thanks for watching, and as always, I'm very happy to receive criticism, suggestions and ideas in the comments. Bye.